I just started recording. I had one of those moments where I was saying, "I hope you enjoyed arithmetic sequences." And I every once in a while, I second guess myself on the pronunciation of that because if I were to tell you, or if somebody were to start talking about addition, subtraction, multiplication, and division, I would say arithmetic. Um, then you're just doing arithmetic. But in terms of the sequence, which is spelled the same way, I believe, I definitely say arithmetic, which makes me sound like I either don't know what I'm talking about or that I'm trying to be stuffy. So anyway, did a quick Google search, and top pronunciation by votes was arithmetic, which is kind of weird, I guess, that it seems a little different, whether I'm talking about um, kind of this very same spelled word in one context or another, both math, but that's what I do apparently. So anyway, I hope that the arithmetic sequences and series went okay. Um, I realized in one of the discussions, and I'll just start off just real quickly talking about this. We had mentioned that 2t1 plus n minus 1 times the common difference times the number of terms divided by 2 was the general sum of an arithmetic series, or the sum of the sequence, I suppose. It is the series. Now, or the partial series sum. So partial series meaning it ends at some value n. Now for this particular one, I could write that a little bit nicer because that's the same as t1 plus t1 plus n minus 1 times d. Now, if I take a look at this part right here, t1 plus n minus 1 times d, that actually is the same thing as just our general term. So it's tn. So that means that Sn can also be described as t1 plus tn over 2 multiplied by n. So if for some reason you know the last term and you just want a little bit of a simpler looking equation to go along with what you're currently doing, this is a little bit tidier looking. It's really the same thing, just you have a substitution in there, but it may be something that you wish to use instead. So just in case that's helpful to you, I don't know if I just mentioned that really. I think I just gave you the one in terms of T1 and D and N, which probably is a little more built on the basic building blocks there of the sequence, but either one's good. So we're going to start talking about a different type of sequence and then series again. So we're going to make a list, an ordered list, and then we're going to start adding a specified amount of terms of those lists. That's what the series is all about. So that's what we're going to be taking a look at right now. So first of all, geometric sequence is one in which the ratio of consecutive terms is constant. So before, when we were adding a constant value, so again, a little bit of an kind of off to the side, but if I had 3, 5, 7, 9, 11, that is an arithmetic sequence. It has a common difference of 2. So I'm adding 2, I guess you could say, in order to get from one term to the next. So we said that that's this type of sequence. Now, what is being described to us on the screen below is a geometric sequence is one in which the ratio of consecutive terms is constant. So ratio, rational fraction. So if we take t1 and t2 and we divide those two things, we're going to get some ratio. I'm just going to call it r for the time being. What this says is that the ratio of consecutive terms is constant. So that means if I took t3 and I divided that by t2, I would also get r. Or if I took t7 and divided it by t6, I would also get r. So the idea is that no matter which, where you are along in the sequence, if you take two consecutive terms and divide the second one, I guess you could say, the the latest one by the previous one, then you will come up with this ratio that is always a constant, always some constant value. That does not happen with an arithmetic sequence. So if I take 3 and 5 and I did the ratio there, that would be 5 over 3, and then the next ratio would be 7 over 5, and that's obviously that already with those two examples, that has not held up, that is a common ratio. That is a common difference, but not a common ratio. So, as I said on the slide down there, this ratio is most often referred to as the common ratio. So just like I sometimes when we were talking about the arithmetic sequence and series, when I was talking about D, I was mentioning the common difference. This time I will talk about R, and that will be our common ratio, and that will come up fairly often. So this, if I just listed T1, is just where we're going to start. Then the second term would be T1 times 1 common ratio. I could just list it as T1 and then T2, of course. Oops, sorry about that. So T1 and then T2 and then T3. But really, since we have this relationship that we know is true, which is T2 divided by T1 is equal to R, as well T3 divided by T2 is equal to R. Well, if that's true, then I could just solve this first one for T2 and say that that is equal to T1 times R. And the second one means that T3 is equal to T2 times R. But I know that T2 is actually T1 times R, which means that this is T1 times R times R. So T1 times R squared. So as you can see on the screen down below, the T1 value would be our first term, T1 times R, because as we said here, that is the equivalent of T2. T1 times R squared would be the equivalent of T3, and of course you're only going to be multiplying by one more common ratio for each consecutive term that you have in there. So it's T1R cubed, T1R to the fourth, T1R to the fifth, etc. So T1 just represents your general first term, R is that common ratio that we were talking about, which means you can see a relationship when you look at those. When you have your first term, the exponent on the R, well, there is no R there. So it's kind of like the R is just a factor of 1. It just multiplies and doesn't do anything. So what exponent on R would cause it to be the same thing as a factor of 1? Well, that would be a 0. So for our first term, we want the exponent to be a 0. For the second term, we want the exponent to be a 1. For the third term, 2. For the fourth term, 3. We always want the exponent to be 1 less than the term number that we're looking at. So what that means is when we go and develop that general, the term generator, Tn is equal to whatever the first term was times the number of common ratios that would take us to the correct term number. And the number of common ratios is always 1 less than the term number itself. So in this case, if you are wanting to go to n, then you would go and take it to the power of n minus 1. One less multiplying ratio than the term number. All right, so let's take this and try to apply it to a situation. One of the things you may have noticed when you were working with an arithmetic sequence and series is arithmetic sequences generally are things that you can associate with linear functions. So linear functions are nice. We deal with them all the time. Oh, good, that's nice. So I'll see if I can save that later if I can remember it. And in this case, you might recognize the type of function that is usually associated with this type of problem. So I'm going to read it. You could, but I will anyway. In nature, many single-celled organisms, such as bacteria, reproduce by splitting in two so that one cell gives rise to 2, then 4, then 8, and so on, producing a geometric sequence. Suppose there were 10 bacteria originally present in a bacteria sample. Determine the general term that relates the number of bacteria to the doubling period of the bacteria. state the values for t1 and r in the geometric sequence produced. So first of all, this is a doubling problem, and you probably think right away, oh, I took Precalc A. This is an exponential function, and it is. So one way to look at this is definitely with an exponential function. That would be fine. So we're looking at it through a different lens right now. And there are reasons why you would want to be able to express things in terms of a sequence or a series. So let's focus on that without trying to overlap it too much with this idea of an exponential function. So I'm just going to write down what I think the first few terms of this thing would be. It says we start with a 10. So here we are, 10. And then we're going to have doubling occur. So there's going to be a 20, then 40, then 80, and it should keep going. And it doesn't say that it ends at any particular point in time, so I'll just put the ... and I'm comfortable with that. Okay, so T1. T1 is just whatever the... I got some pretty colors here. I'm going to go with that. T1 is just whatever the first term of the sequence is, which we started at 10, so T1 is 10. Now I can tell from my list, or I could tell from the wording of the problem, that doubling means that the common ratio, or the number that I multiply by every time to get the next term, is 2. So I would have a common ratio of 2, which means that if I wanted to express a Tn here, Tn is equal to T1 plus, T1 times r to the n minus 1. My apologies, my arithmetic brain was taking over. So in this particular case, we are going to say that Tn is equal to 10 times 2 to the power of n minus 1. So if I wanted to know, for instance, term 4, which is something I should know, it's 80, that would be 10 times 2 to the power of 4 minus 1, which is 3. So 2 to the power of 3 is 8, multiplied by the 10 that's already there, we get 80. That's good. That's what's up there. So this would allow us to skip, and if I wanted to know the 100th term here, not that that sounds like a great idea, but if I wanted to know the 100th term, it would be 100 times 2 to the power of 99. So that's quite a nice, tidy expression. And my wife was peeking in the window at me and making me all self-conscious. So the 10 times 2 to the power of 99, you could throw that into a calculator. Of course, 2 to the power of 99 is a huge number, which is kind of awkward, but that's okay. That's not a big deal there. But you would be able to find out what that value is. One of the things, if these are growth ratios, so we'll talk a little bit more about that when we do infinite geometric series, which will be coming up in probably in the next video. If it's a growth type sequence, which means that the r value is going to be either greater than 1, or you could do less than -1. You could have a flipping and growing number, and that would be okay. But if that happens, the values get really big eventually, because it's an exponential function. Exponential growth is something that eventually it just becomes very, very, very fast. So this becomes a huge number. If you're doing something similar to an so let's see if I have an arithmetic. I didn't. Well, I do. I have that 3, 5, 7, 9. That would be, just as a little aside there, Tn is equal to 3 plus a common difference of 2 times n minus 1. If I were to put 100 into that, it's 3 plus 2 times 99. 2 times 99 is just 198, plus 3 is 201. That's a really reasonable number. This number here, 2 to the power 99, I don't even have a clue as to exactly how big that is. It's a very large number. So the numbers do grow very quickly in this particular type of problem. But all we were asked to do here was identify T1, identify the R value, and identify Tn. We've done all three of those things, so that's great. We can move along. So if we were asked to determine a particular term. This is very similar actually to what I just did with saying T100, which is fine. I'll just do this example as well. This says sometimes you use a photocopier to create enlargements or reductions. Suppose the actual length of a photograph is 25 centimeters and the smallest size that a copier can make is 67% of the original. Now 67%, I am like super tempted and I want to use 2/3. And I know that that's not really 67%. It's very close to it. But nice fractions, always better to use, especially in a case like this where you have basically repeated multiplication. So this is after 5 reductions, so that's going to be to the power of 5. 0.67 to the power of 5 is icky. 2/3 to the power of 5 is really pretty tidy. So I don't know. I'll just I'll say that it's 0.67, and I'll have to break out a calculator for it if I can find one kicking around, because it's not the nicest thing. All right. So first of all, I want to express this as Tn, and eventually I want to write down what T5 would be. Now, there's little tricks to something that's going to go on, and I hope you're already wondering about this. Is 5 reductions the 5th term? So I'm going to leave you to thinking about that for a moment while I set up the problem, and maybe you can pause it and give it a little more thought if you want to. But you want to be able to identify whether the number in the problem is actually the term number or if it's something different. So let's go ahead and say Tn is equal to T1 r to the n minus 1, which means in this case Tn is equal to 25 centimeters. I'm just going to use centimeters as the unit. I could write in centimeters, but I'm going to be a little bit lazy math-wise. Just write down the number and say that is multiplied by 0.67 to the power of n minus 1. Now, the problem is that if I put in a 1 for my n value, so what is my T1? Well, it's 25. How many reductions have taken place at the 25? Well, it's the original, so that's actually 0 reductions. Now, I could probably pick my T1 to be 0.67 times 25, and then everything lines up, and that would be okay. But I decided not to. I put 25 down as my original. And so because of that, I need to recognize that when I want 5 reductions to take place, 5 reductions for me is actually looking for T6. Now, as I said, you could set this up a little differently so that this value right here was actually 0.25 times not 0.25, it's 25. I already discussed that I was going to keep it in centimeters. So 25 times 0.67, and that would be okay, and that could be your T1. And then you have another 0.67 to the power of n minus 1 that is multiplied beside that. But, as I said, the way that I've set it up, for 5 reductions, I actually want that to be expressed as 25 times 0.67 to the power of 5. So 5 reductions, 5 of these 0.67s multiplied in. That makes a lot of sense, but it's not an n value of 5, which kind of goes against some of the other setups that you'll see. So you have to use a little bit of logic sometimes in terms of not just assuming that the number that's in the problem is n, depending on how you've set it up. All right, so this is good. I probably should get a number there rounded to the nearest tenth of a centimeter. I'm going to grab a calculator. So 0.67 to the power of 5 multiplied by 25 be 3.4 rounded to the nearest tenth. So we would be able to, after 5 reductions, reduce this to 3.4, and then it would be in centimeters. So after, I don't know how I'm going to write this down, but I'm going to, after 5 reductions, image size would be 3.4 centimeters. I should say approximately, maybe rounded to the nearest tenth of a centimeter. All right, so again, we can just find some later term value without finding the ones in between. One of the benefits of being able to write a general term generator. So in this case, the general term, Tn is equal to T1 times r to the n minus 1. All right, so this one, we're going to be given some more random information. So we know T3 and we know T6 in this particular question. And we're looking to find eventually T1 and r. So we have T3 is equal to 54 and T6 is equal to negative 1458. So what we have here is T3 is the same thing as T1 times r to the n minus 1, but our n value for that one is 3, so it's 3 minus 1, which is 2. And T6 is equal to T1 and then r to the n minus 1, which is r to the 5, actually. So I could say that 54 is equal to T1 r squared, and negative 1458 is equal to T1 r to the 5th. Now this may be, and I could be wrong, but this is a type of two variable, two equation system, but it's not a linear system in that we're not going to be able to subtract or add some multiple of one of these equations from the other in order to cancel out either the T1 or the r, either squared to the 5th power. So this might seem a little bit weird. But what I'm going to do instead is I'm going to label my first one here as being equation number 2, and then this one, 1, and then this one's going to be equation number 2. And I'm going to take equation 2 and I'm going to divide it by equation 1. And the reason why I might be interested in doing that is because I have T1 as a coefficient in both of those equations on the right-hand side of the equation. So if I have a coefficient of T1 and I divide it by something that has a coefficient of T1, then those coefficients will cancel each other out. So on the left-hand side of the equation, we would get negative 1458 divided by 54. And then on the right-hand side of the equation, we would get T1r to the 5th divided by T1r squared. So again, I'm not even going to bother trying and making a fool of myself again. All right, so negative 27. Probably could have guessed that it was a perfect cube, but hindsight's 20/20. Negative 27 is equal to T1 divided by T1, gives us this canceling out. And then we have r to the 5th power divided by r squared. So r to the 5th power divided by r squared, the way we can tidy that up is you subtract, you have the same base, so you subtract the exponents. So you have r to the 3rd power. Take the cube root of both sides. Cube root of a negative is going to be negative. And then cube root of 27 is 3. So it would be negative 3 is equal to r. So we now have the common ratio. I also have a little equation that says that 54 is equal to T1 times the common ratio squared. And my common ratio I just found out was negative 3. So what we could do there is take the negative 3, square it, that's 9, divide 54 by 9 and get 6. And so my T1 is equal to 6. So in the end, if we are looking for T1 and r, we have them both now. And so our sequence, which it doesn't ask for, but our sequence looks like this: 6, negative 18, 54. Woo, so negative 162, and then I'm going to probably stop there. It's going to keep going. Great. Okay, so that's pretty good in terms of seeing how a geometric sequence behaves. Now, geometric series are, of course, the addition of, in what we are doing and what we've done, and I should have used this language in the last video that I did, we are doing partial sums. So what I'm trying to express is the Sn is the sum of the first n terms. So it does not mean we are summing up an entire sequence. We are stopping the sequence somewhere at n and summing up those first n terms. So this is a partial sum. And this partial sum is basically, it's the sum from I is equal to 1 to n of, I'm just going to say Tn. So that's a really lazy way to put it. But it basically says, hey, add the first term, then add the second term, then add the third term. Stop when you get to n. Actually, it's Ti in this case. That's lazy, but is also wrong. So in this case, it's the I that's counting, so it's going up. Some people will put a K if they don't like the I in there. I and K are both very common counters. So again, this is sigma notation, and all it means is that we are going to repeatedly add whatever the new version is of the thing that's inside or beside the sigma. So what we do is everywhere where there is an I, we would replace it by the current value of I. I always starts at the bottom number in terms of what's lined up in the sigma notation. So in this case, it says I is equal to 1 is the start. So you start at a 1, and so that would mean, hey, the inside is T, and I replace the I by 1, so it's a T1. And then this symbol, this sigma notation, means you're going to add to that the next one. What's the next one? Well, you always actually increment or increase the I value by exactly 1. So it would be added to T2. So add T2, and then add T3, because that's the next increment, add T4. And you are going to stop, though. We are going to stop this particular thing when you get to Tn, because that is the top number, and so that's the last thing that we're going to add, which means that this is the partial sum of the first n terms of whatever this particular sequence was. Now, if the sequence is our fun little sequence that is made up of Tn is equal to T1 r to the n minus 1. Now, I put that instead of Ti. I probably should have put it as Ti. You know what? I will. Even though it's going to look different from what we just developed and are used to, just because it's going to be Ti instead. So if I could say Ti is equal to T1 r to the I minus 1. But anyway, it doesn't really matter. So that's what it looks like in a summation notation. Very, very, very general. Now, let's write some of this down in a non-summation notation sense. So I'm going to actually write that Sn is equal to, and then this kind of bleeds into, so this is the general idea. This is going to bleed into what's on my next slide, which is called a telescoping series. Now, I will, I'm going to write down what Sn is. 1. Oh, not 1. Wah, wah. T1 plus T2 plus T3 all the way up to Tn. Now, that is very general. For us, that's T1 plus, yeah, I'm going to put it at the end. So T1R, usually a common ratio. In a lot of things, we put coefficients out front. I'm going to put it at the end. So T1R plus T1R squared plus blah, 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 T1R to the n minus 1. I don't know if you can see that very well. I'll try to make it larger for the next one. Okay, now I'm going to use a trick, and it's not an obvious trick, so don't feel don't feel like this should be intuitive. I'm sure, I actually don't remember the history of this one, but I'm sure at the time it was probably somebody very, very bright that thought about it for quite a little while and came up with a neat solution to it. One that over time, math people are like, oh yeah, this is simple or whatever, but it's not necessarily an obvious step to take. So I'm going to, instead of writing that exact same equation that I have on the line above, I'm going to take it and I'm going to multiply it by r. So I'm going to have, and I guess I should keep it on the same side. So this is Sn times r. That's equal to T1, can't write, T1 r plus T1 r squared plus T1 r cubed plus dot 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 plus, normal plus, I don't know why I'm putting a squiggly there, T r to the n minus 1 times another r, which means I'd add 1 into the exponent, so it becomes r to the n. Now, the really neat thing here is I'm actually, just for the sake of things looking a little bit tidier, well, never mind, I'm going to leave it the way that it is. I'm going to call this one equation 1 and this one equation 2. These are telescoping series, and what that means is they have an undefined number of terms, n. However, the inside of these series are identical. This single term is unique in the Sn series and appears nowhere in the Sn times r. This term down here, which it should have a little 1 next to the t, is also completely unique. However, every other term is going to have a copy of that term in the other statement. So if I do something really sneaky, like take one of these and subtract the other one, I am going to have every single one of those middle terms completely cancels out, which is really cool. So we would have Sn times r minus Sn. Probably should give myself a little more room. And then that's going to be equal to 2 minus 1. So I have a T1 r to the n that is unique and not canceled out by anything. Everything else, I'm going to technically be taking this and subtracting the copy, this and subtracting the copy, this and subtracting the copy. 0 every time. At the end, though, there's nothing here to subtract this from. There's no copy, so I just end up having to subtract the T1 at the end. So we turned something that was an unspecified number of terms into, right now, I have 2 terms on the left-hand side of my equation and 2 terms on the right-hand side of my equation. So if I factor out Sn, which is common on the left-hand side, I'm left with r minus 1. And that's going to be equal to, T1 isn't common on the other side, r to the n minus 1. Now, I'm going to do something a little bit strange because I'm used to, I think, seeing this the other way. So if you subtract 1 from 2 instead of 2 from 1, which I thought about doing at the time, you might have heard me say, oh, no, I guess I'll be okay with that. Typically, I see this written the other way most of the time, I think. It's not that it's wrong this way, But if you see this instead, it is the exact same statement. And the reason why is because you would just factor a negative out of the numerator and a negative out of the denominator. And if you do both those at the same time, you just get a negative divided by, or negative 1 divided by a negative 1, cancels out. And so these two are equivalent, totally equivalent. But it may look a little different. And so if you're thrown off, then it doesn't really matter which way you write it. Actually, to be honest, you may decide that it is just easier to write one versus the other. This one you end up with negatives a lot of the time with nice numbers, so it kind of is a pain in the butt. Not that it really matters to have the negative pop up. You might find this one, just subtracting 1 from a couple of things, is a little more intuitive. I don't really care. Just didn't want you to get thrown off if you see it in the textbook and it's written the other way around, which I think it is, but I can't remember off the top of my head. All right, so that was using a telescoping series. This idea of having one of these series that basically fits around the other series except for the very end. And so we've pulled it or telescoped it out. And what we're left with is this little piece at the end here that is out by its lonesome. The entire middle is overlapped, and then you have the little piece that's out on the other end. And what that allowed us to do was when we subtracted them, we get this really cool little expression, which is the general summation of the sequence, the geometric sequence, or otherwise known as the geometric series. So partial sum. So we can use that in order to develop solutions, I guess, to these little sequences or series. So in this particular case, it says determine the sum of the first 10 terms of each geometric series. So let's go ahead and do that. So what do we know in A? Well, our first term is 4. Our common ratio should be 12 divided by 4, which is 3. Now, let's just double check that. 12 times 3 is 36. Great. It tells us in the question that it's a geometric series, so it'd be really bad if it wasn't. It's going to be misleading, but you never know. So it's good to just test it real quick. So this one says the first 10 terms, the sum. So this would be S10 is equal to, and this is what we just had developed above. So it's T1. Now, I'm going to put S, I'm going to change that for a second. We are looking for S10, but I'm going to write Sn down first, just for practice. So T1, 1 minus r to the n over 1 minus r, which in our case, this is S10 that we want to use. Excuse me. So this is 5 times 1 minus r to the nth power. So that's the 10th power. So 1/2 to the 10th power over 1 minus, I got totally thrown off. My apologies. I started looking at B. I am going to replace this by, we're going to do that in just a second, but I'm going to replace it by A. I just started looking at the wrong spot. So we would have, my apologies, T1, which is 4, 1 minus common ratio, which is 3, to the power of 10 over 1 minus common ratio, which is 3. All right, so the sum of the first 10 terms, 3 to the 10 is not something that's kicking around my head right away. So yeah, of course, 59,049. That's kind of a nice number. So I'm going to put that together with the 1 divided by a negative 2 and multiply it by 4 and get that the sum of the first 10 terms is going to end up being 118,096, which might seem a little bit unbelievable. I usually don't like to do this where we do it out by hand to kind of check because the numbers are quite large, but I'm going to do it this time just so that you can see that this maybe isn't as unreasonable as you may think. Because these numbers are increasing by a factor of 3 every time. So they do end up getting pretty large pretty quickly. So what do I have so far? So that is 7, 8, 9, 10. And so now that you see that last number being almost 79,000, and that's added to 26,000, you probably are feeling a little more confident that we are going to be able to reach a number such as 118,000 in 96. So that's anyway, I thought I would do it out that one time, just so you can see that the exponential growth that's occurring here is in fact making a very large difference in making our values become very big for sums very, very quickly. All right, so I will do B as well. So this one is kind of funny because they just give us T1 and they give us R. So we just go ahead and do it. S10 is equal to T1 1 minus R to the N, which is 10, over 1 minus R. So in this particular case, I am going to do it as a fraction, I think. So that's 2 to the power of 10 is 1024. So it's 5. And then 1 minus 1 over 1024 over, and then that's just a half in the denominator. So up top, we would get 1023 over 1024 times the 5 that's still out front, times 2. Dividing by half, the same thing's multiplying by 2. And so we would end up with 10 times whatever's up top. So something like that. Now that reduces. I'm going to actually just see what that number is. Obviously, it's a touch less than 10. But it is the number 9.9902, so it's very, very close to the value of 10 there. Now, this is actually something that we're going to see in infinite geometric series. So if I take 5 and I add half of 5 to it, it becomes 7.5, and I add half of 2.5, it's going to become 8.75, I think. And then you add half of 1.25 to that, and then it's going to get very, very close to that value of 10. And so after 10 terms, we're already very close. Ooh, that light is not so friendly for that. Very close to that value of 10. All right, so let's continue on, and I think this is the last little piece, and then we will be done. So determine the sum of a geometric series for an unspecified number of terms. Okay, so don't know what the n value is for these, but we do know the beginning term is 1 over 27, and the end term here, I'm going to put the dot, dot, dot a little earlier, is 729. So what I do know, T1, and I know Tn is equal to 729. And I do know the common ratio because I have consecutive terms there. So the common ratio is 3. So if I multiply 1/27 by 3, I get 1/9, and then I multiply by 3 again, I get 1/3. So that looks good. Let's just put down. It says to determine the sum, so I'm just going to say, well, what would Sn be? So Sn is equal to T1, and that would be 1 minus R to the n over 1 minus R. Now, what I'm going to do here is I'm actually going to trying to think of the tidiest way I could do that. Tn is equal to, it would also be true, that it would be equal to T1 times r to the n minus 1, which then means that Tn divided by T1, and then if I multiplied that by r, it would be equal to r to the n. So I could replace the n in this part of the equation by T1, Tn over T1 times R, which I'm going to do and see how it tidies up. So Sn is equal to T1, and then it would be 1 minus Tn over T1 times R, and then that is good, and then over 1 minus R. So that's equal to T1 minus Tn times R over 1 minus R. Now that's actually a kind of a tidy looking equation comparatively. So let's fire that through and see if it makes sense, and then I'm going to double check it kind of using means that aren't like this. So we would say that the sum up to n, which we don't know what the n is going to be equal to the first term minus the last term times the common ratio over top of the 1 minus the common ratio. All right, so do I really want to? Yeah, I guess I should. So 729 times 3, I'm going to say 1027, but ooh. All right, so 1 minus that would be negative 59,048 over 27, all over negative 2. So that would be the same as the negatives will cancel. And then I'll have 27 times 2 is 54. So 59,048 divided by 54. So 59,048 divided by 54 equals about, I suppose, so about 1093.5. Okay. So that means that the we could work out, well, it doesn't even say what we need to do there for the n, so that should be fine, just to leave it as is. Now we could work out what the n value is and do this in a different way. Let's do that too, just to kind of verify. So if I said that our T1 is equal to 1 over 27, and our Tn is equal to 729, and our R value is equal to 3, then we could say that Tn is equal to T1 times R to the n minus 1. So our 729 is equal to 1 over 27 times 3 to the n minus 1. So we're going to take 729, multiply it by 27, and then I'm going to get that value then is equal to 3 to the power of that. Now, I'm going to use logarithms actually to bring that down. So I'm going to get the natural log of 19,683 is equal to n minus 1 times the natural log of 3. And so natural log of that larger number divided by the natural log of 3 gives us 9. And that's going to be equal to n minus 1, which means our n is 10. So once we know that our n is 10, we could do the partial sum up to 10 using the traditional formula, which was T1 times 1 minus r to the n over 1 minus r, which is T1 is 1 over 27 times 1 minus, what was it, 3? 3 to the power of 10 over 1 minus 3. So again, I'm going to, that actually looks really familiar. So it looks a lot like this. A lot like this. So the question is 729 times 3 the same thing as 3 to the power of 10? So 729 times 3 is 2187, and 3 to the power of 10 is not. Oh, haha. The 1 over 27 multiplies into that. Whew. Okay, so the 1 over 27 would be multiplied onto this and this. So then we divide that by 27, and we get 2187. My apologies for that. Set us up for failure there. But this is, in fact, the exact same value as what we got up here, because we would get the 1 times the 1 over 27, which is, this piece right here. And then we get the next piece, which is the 2187, which is when you multiply this into the second part. So if you keep going here, evaluate that number, we're going to get the same sum both this way and this way. So for one of those, I decided to kind of come up with a new equation, I guess you could say. So we just said, generally, if you wanted to express this r to the n thing as something else, we could rearrange the general term in order to get rid of that requirement to know what n is directly. So then we could make a new equation that looks like this, and that would be really nice. You probably want to tuck that away somewhere just in case you want to pull it out. You do not have to derive it every time you want to use it. The other option here is to kind of work your way through it only using things we had directly developed so far, figure out what that n is first, and then know that your partial sum is only up to a value of 10, and that works too. So let's just do this last one. Obviously, T1 is equal to 4, and the common ratio is -4. So it flip-flops, and this series actually goes positive, negative, positive, negative, positive, negative, positive, negative. It ends on a negative, so we would expect the sum to be negative. If it ended on a positive, we could expect the sum to be a positive. Now, if I take the partial sum, which I don't know what the number of terms is, but I do that as 4 plus negative 65,536 times the r value, which is -4, divided by 1 minus the r value? What? Is that actually true? Let's go back up there. So that would be T1 minus Tn times r minus, I was thrown off by the sign that I was going to get. I remembered the equation wrong. So it was a mistake on my part. You get T1 minus the Tn times r. So sorry to flip-flop all over the place here, but up here is what we're using. T1 minus Tn times r over 1 minus r. All right, 1 minus r. That gives us 4 minus very large number. I probably actually should get rid of the 4 and just do it all at once. So 4 minus all that stuff, which is a negative and a negative. So 65,536 times 4. That's negative 262140 divided by positive 5, which would give us in the end negative 52,428. Now, I'm going to try to explain to you why that seems kind of reasonable. It's because the previous number to the negative 65,536 would have been positive, and if we divide that by 4, it would have been 16,384. So if I take that 16,384 as a positive and I subtract 65,536 and I ignore everything else, I'm going to get negative 49,152, which is actually really reasonably close to that. So even not including all the other ones to kind of hone it in, that makes sense that it should be a number that is not as negative as negative 65,536. But anyway, so good stuff. We ended up there with our sum for an unspecified number of terms by using this kind of new formula. All right, I think that is all I wanted to do. Yeah, that one's okay, but it's not really. Anyway, you know what? If you want to pause it, try it out, and then you can ask me what the answer is sometime, either by email or by joining me during office time. So if you want to try that out, it's not that one's actually not too hard, although it's got a lot of words there, so it might turn you off. All right, I wish you all the best. I hope things are going okay, and hope you are still clicking along with some of the math that we're doing. If you have any questions, please let me know. Take care, folks.